1903, a Russian rocket scientist by the name Konstantin Tsiolkovsky published this equation, which goes by various names like Tsiolkovsky rocket equation, or the ideal rocket equation, or the rocket equation, or sometimes the classical rocket equation. But what are these parameters in this equation? Well, if we look at this equation, it actually consists of delta V, which is the final velocity that one wants to achieve with the rocket. It contains VE, which is the exhaust velocity, which represents the velocity at which the rocket throws out propellant through the engine, times the logarithm of the initial mass divided by final mass. Looking at this equation, we can actually see that the final velocity of a rocket is actually just dependent on the exhaust velocity and the mass ratio. And this is true, and during a rocket design, much time is actually taken to actually improve the exhaust velocity, because in most cases, the change or delta V needs to be known, because we need to know whether our rocket will actually escape gravity or not. So, where does this equation come from? Well, to understand this equation, we have to travel back in time to 1687, because Newton has published something that we need. In his second law, it tells us that force is given by mass times acceleration. And acceleration is just a derivative of velocity itself. So if we substitute acceleration into Newton's law, we actually find that force is just given by mass times the derivative of velocity. But during Newton's time, he didn't have to deal with a rocket where the mass actually changes with the time. So expanding Newton's law to actually accommodate a rocket would just do force should be given by the derivative of both the mass, velocity, over time. Okay? And the change in mass of a rocket is just actually the amount of propellant that has been used. So we can actually say that the force or the thrust in a rocket is actually given by the mass flow rate times the exhaust velocity, which is just the velocity at which the propellant leaves the rocket engine. So, we understand this for this part. Let us go back to Tsiolkovsky equation and actually see how to derive it. From Newton's second law of motions, let us substitute acceleration this way so that we can manipulate it to get the rocket equation. Just like we saw that acceleration and velocity are actually related, we can actually get that velocity should be an integral of acceleration. With our substitution, we can get this. But remember the equation that we derived from Newton's equation, this one. It tells us that force is given by mass flow rate times velocity. We can then go ahead and substitute for the mass flow rate in our equation, and then we have this. But we know that in a rocket that the mass changes over time, and that this mass can actually be given by the initial mass minus the mass flow rate times the given time t. So we can then go ahead and substitute for the mass flow rate to actually get that the change of velocity will actually be given by this. And some calculus magic, we actually get that the change in velocity will be given by VE, the natural logarithm of this. But looking at this denominator, we see that this can actually be the final mass of the rocket. So we can actually just go ahead and substitute this for the rocket equation. And this is how you get the rocket equation for Sokov's